Metathesis reactions, as you recall, this is the fourth in line of classifications of reactions. Just to review, combination, simply A plus B goes to AB. Decomposition, where is the reverse of the composition, as we know. Then the single replacement, where A replaces A as an active metal, replaces a less active metal to form a AX plus B, as shown there, and of course that requires the activity series. And then, as today's work depends upon the double replacement, also known as the metathesis, which is AX plus BY goes to AY plus BX. And so we have on the reactant side ionizable components which exchange ions depending on the formation of what we call a driving force, or a stable compound that is insoluble, or is a weak electrolyte, or a gas decomposition. So this depends upon a driving force. One of three forms: an insoluble, precipitate, weak electrolyte, which we'll talk about today, which is a weak acid or weak base. I'll show examples of each of these in a few minutes. And then from one of the weak electrolytes, except for one, there's a gas decomposition product. Now, the function of each of the driving force classes is to prevent the reaction from going back in the reverse direction. So your ability to identify not only the components of the products, but also to identify what kind of driving force it is, whether it's an insoluble precipitant, a weak acid or base, or gas decomposition. Look at number one here and see how we do. Okay, which of the following would not be a driving force in a chemical reaction? What's a driving force? It is a compound which tends to form in a more stable condition and is a product that pulls the reaction to completion. Form a complete reaction and prevents. You can also use it in that context. Prevents reaction from reversing. I gave you an insoluble precipitate a weak acid, gas decomp, strong acid, or strong electrolyte. So these three are driving forces, classes, and this cannot be. The reason strong electrolytes remain ionized 100%. There has to be the formation of a bond in such a strength, with such strength that it either falls out of solution insoluble or bonds so that it's a weak electrolyte, and I'll explain that in more detail in a few minutes, or it forms a weak electrolyte that decomposes and gives off a gas, much like putting baking soda into a solution of vinegar. You see, effervescence of that. So this one is D choice for those keeping score. Any questions? Next one is, which of the following is classified as a double replacement reaction? Well, the empirical relationship is AX plus BY goes to AY plus BX, with one of the components on the product side being a driving force. Well, the listing was a composition, decomposition, single replacement, and the last one in the list was a double replacement. So the D choice in this was lead nitrate, and potassium chloride goes to potassium nitrate, also aqueous, and the driving force is lead chloride and is a precipitating mercury, silver, lead halides are insoluble, and that represents the driving force of that reaction. Okay. Number 3, which compound in the following reactions is a driving force? Well, if you look at the solubility table, let me write the reaction, then we'll make a decision. Okay. And so we have the following: 2Na3PO4. That's going to be aqueous. I didn't put aqueous or state of existence because that's part of the decision process, but I am now. Nickel chloride, that'll be aqueous, goes to 6 sodium chlorides, and that'll be an aqueous. Nickel phosphate. In there. Just a few footnotes. You will not find the driving force on the reactant side. That's what a driving force means. This pulls the reaction to completion, so be sure on major exam day you look on the product side and find the driving force. Well, how do we identify a driving force? Well, you look at each one of them and see if it is one of the 3 classes. Well, this test deals exclusively with precipitating driving forces. Well, the first one is sodium chloride. Well, sodium chloride is a halide, and all halides are soluble. And the exception is mercury, silver, and lead. I call them happy halides, HAP. You can remember mercury, silver, and lead, HAP. Anyway, if it is a mercury halide, fluoride, chloride, bromide, iodide, mercury, or silver, fluoride, chloride, bromide, or iodide, or lead, fluoride, chloride, bromide, or iodide, it's a driving force. But if it does not have that one of those 3 in the compound, it's not a driving force. So sodium is not a member of that collection, so therefore it is not a driving force. Well, that doesn't mean the other one's a driving force. Sometimes you can, and I throw these on the exam, you can switch ions, neither one of them will be soluble, which would give you a no reaction. So be wise to that, please. Okay, and so it's kind of a curveball where you get one that's not a driving force. Don't assume automatically the other one is the driving force. But in this case, we have phosphates, and if we look at the issue in the second table, all phosphates are insoluble, which means that is a driving force or will precipitate, except for group 1A and ammonium phosphates. Well, that's obviously not an ammonium phosphate, that's a nickel phosphate. So that throws that one out, and nickel is a transition metal. So that compound is, in conclusion, is a driving force, and it is a visible precipitant. If you mix those two solutions together, you'll get a big white cloudy solution or slurry out of the system. Okay, so in the list, nickel phosphate is D choice in there, and so the biggest issue is, can you read the table and determine from the table and the equation what the driving force is and what isn't the driving force? That's the issue. So consider the following reaction with lead chloride as a driving force. What are the spectator ions? Well, lead and chloride are driving force, and there are only two others left, and so that's sodium and nitrate. So let's jot down the equation. 2 sodium chlorides, aqueous, plus lead nitrate, 2 aqueous, goes to 2 sodium nitrates, of course that's aqueous, and the lead chloride is the lead 2 chloride, that is the driving force. So if that is the driving force, then the other compound in the equation remains in ionic form. That is, the sodium ions and NO3 ions do not react. So they are the spectator ions. I guess. Okay, so that is, it's like B choice in the collection. And finally, okay, now the problem is to predict the chemical formulas as well as, in the products by converting these by double replacement. Well, we have sodium sulfate. Well, sodium and sulfate go together real nicely like that, but sodium is a minus +1 and a -2, which will require 2, and so we'll need a subscript there. And that's going to be aqueous. And then barium nitrate. Barium is a +2, nitrate's a -1, so we'll need 2 of those, so we need it in parentheses, and that will be an aqueous. And so we AX, B, Y. Just for your review, AX and BY. And I showed you that if you will connect the inside and the outside and balance the charges, then you'll have the proper compound. So sodium hooks up with a nitrate. And remember, the only subscripts you can take to the product side are those that are associated with polyions. Just because it has a 2 sodium, for example, right here, doesn't mean it's going to be a 2 sodium over here. For example, this is a +1, -1, so that is the correct compound. The only difference is the coefficients, and we balance that if we have to, and that's going to be an aqueous component, and the remaining component is barium sulfate. Barium sulfate is the driving force in that, which is a +2 and a -2. So we need a 2 right there, and looks like we've got most of it B. So that's kind of the decision process in going through a metathesis reaction, and that is a choice in here. Now this is the molecular equation for this. I'm going to go through the ionic equation, that's why I moved the slide up, and the net ionic equation just for your review, and so that you'll have this in your notes if you wish. Make sure we've got a balance. We've got 2 sodiums and 2 sodiums. We've got 1 sulfate, 1 sulfate. We've got 1 barium, 2 nitrates, and 2 nitrates. So we're balanced. So we move to the ionic equation. Now everything on the reactant side you assume is ionized. And assume in test day that I give you the correct compounds. So there's not a matter of guesswork there. So we have 2 sodiums, and they're going to be in solution, and a sulfate, that's 2-, that's going to be in solution. Barium, that's going to be in solution, +2 + 2 NO3 aqueous ions, and then that will go to the product side. 2 sodiums aqueous plus 2 nitrates aqueous. Then the driving force. Now remember what I say, the driving force, and then you'll see today weak electrolytes as driving forces, and you will see some on the reactant side in the acid bases that are not ionized, not shown in ionic form. I'll show you those, but in this case it's a precipitating driving force, and you leave it in that form. Do not show ionized driving force. Now this is the ionic equation, and so looking at the left side against the right side, we find that sodium and the nitrates are identical and are the spectator ions. So when we write the remaining components, the net ionic equation, the net ionic equation shows those components which undergo reaction. Again, net ionic shows only those components which undergo reaction. Now, by convention, the metal is typically written first. Honestly, it's not double negative. It's not incorrect if you put the negative first and the metal second, non-negative, but most people will go with the metal simply because it's first on the periodic chart. Showing those components which do react.